Okay, so can everybody see the screen? Yes, no? Okay, good. Thank you. Okay, so for the midterm, I also uploaded the video recording of the discussion of last midterms answers. All right, because quite a few asked to review them, but we currently don't have any slot in the lecture schedule, okay, to do that. All right, so I uploaded the video. If looking through the video you still have doubts about any of the questions, then you can email me or contact me separately, and then we can discuss. Okay, so let's carry on with the discussion from where we left off. Okay, so in the last week we were talking about this hyper period. All right, so basically what we saw was, okay, in a situation like this, so basically we're talking about the rate monotonic scheduling approach, where a task with the shortest period, all right, which is also considered to be the shortest deadline, will have the highest priority. All right, and if you look through and you try to analyze the sequence, all right, if I can map out the entire sequence for one hyper period and I do not see any issues, there are no deadlines being missed, then there is no issue in keeping the current priority as it is. All right, that means it is always schedulable. Okay, you will not miss any deadlines. Okay, so this is what we stopped. This is where we stopped last week. So the hyper period is basically the least common multiple of the task periods. All right, so this is stop. Now let's go on. All right, so what is schedulability analysis? All right, so it is basically telling us that there is a feasible schedule, okay, if all the deadlines can be met, that means all the timing constraints can be met. All right, an optimal scheduling algorithm is one that produces this feasible schedule. All right, so the scheduling algorithm, there can be different types. Okay, so an optimal one is one that produces a schedule that is able to fulfill all the timing deadlines. Okay, this RMS is considered optimal fixed priority scheduling, because if you take, for example, this situation where I have three tasks, T1, T2, T3, and I randomly, okay, go through all the different possible permutations, okay, of assigning each of these tasks to a priority level, okay, high, medium, and low, and I try out which one works. All right, and if let's say I find that two of them work, for example, this combination and this combination work, all right, what we can say is one of them, okay, will be RMS. Okay, so if I were to take any random assignment and try it out, and I happen to find one or two that actually works, you can be guaranteed that one of them will be RMS. Okay, so as long as you follow RMS, all right, you can be guaranteed to pick one schedule that actually does fulfill all the timing constraints that you have. Okay, so that is the good part of RMS. You do not need to try out all possibilities. Okay, so for example, if I have n tasks, I have n factorial different possible permutations of the task assignments. All right, but you do not need to try everything. If you follow RMS, RMS will definitely give you, if RMS can give you that uh, scheduling that fulfills all the deadlines, then definitely it is guaranteed to work. Okay, so you do not need to try out different possibilities to see if it works. If RMS is guaranteed to work, then it will definitely work. All right, so that is a good part of RMS. Okay, so of course, what can we do in terms of analyzing the schedulability of multiple tasks? All right, so one of the things that we want to do is we want to be able to predict the worst case behavior. All right, when you apply a particular algorithm. Okay, so now I say I want to apply RMS. All right, so what I want to do is I want to look at the worst case behavior and see in that situation, can I still fulfill all the timing requirements given this scheduling algorithm that I'm going to apply. All right, and to do that, there are a few different approaches. The first one is we measure what we call the utilization of a task set. Okay, and the utilization is basically what fraction of the processor time do I actually use in this particular task. Okay, so I can have many different tasks, all right, and in a multi-threaded system, the processor is dividing itself amongst these various tasks. Right? So what percentage or what fraction of processor time am I actually using for a particular task? And I need to add them up all together. And that is what this formula does. Okay, just a summation of for each task, I take the computation time over the period. Okay, so that is the worst case execution time over the period for all the tasks, and I sum them up. Okay, and basically as long as this value is less than or equals to 1, then you can say that it is possible to have a feasible schedule. Okay, that means this basically tells us that the processor, when it divides its time among all the different tasks, it is still able to satisfy all the requirements. All right, based on just computation time and the periodic interval of the different tasks. So it is a necessary condition. Okay, because if this is greater than 1, that means I actually require more computing time, okay, than what my current tasks are actually getting. All right, that means I need more time, all right, which I'm not getting. So u less than equals to 1 is a necessary condition. Necessary means I must have it. Okay, so I must have it in order to make sure that I can actually use this current scheduling framework to divide the time among all the different tasks. Okay, if this condition is not satisfied, it is not possible at all to have any form of feasible schedule. That means you will never have enough time to complete all the things you want to do. All right, so this is a necessary condition. But at the same time, it is not a sufficient condition. Okay, so sufficient means it is enough. Okay, but so u less than equals to 1 is necessary, that means you need it, but it is not enough to just say that just because I satisfy this condition, I can have a feasible schedule. All right, so this is important, the words you must understand. Sufficient condition means if the condition is satisfied, then the schedule must exist. Okay, but in this case, u less than equals to 1 is not a sufficient condition. Okay, so let me show you an example that is easier to see this. All right, so if I look at this task over here, these two different tasks, if I compute utilization, so utilization is basically, in this case, 2 over 5 plus 4 over 7. Okay, so you'll get 34 over 35, and that is less than equals to 1. All right, if I take these two tasks and I were to draw out the timing, okay, so let's assume that I follow RMS scheduling and I say task 1 is higher priority, correct? Task 1 runs first. So after task 1 runs, for 2 units of time, I switch over to task 2, okay, but since the task 1 period is up, okay, 5 units of time, then the next iteration of task 1 is to be run, so I get preempted and task 1 runs again. All right, and by the time I can come back to task 2, okay, the deadline of task 2 has already been met, and I have not completed task 2. Right, so this is using the RMS approach, correct? The shortest deadline is highest priority. Okay, but at the same time, if I were to try the other option, okay, I only have 2 tasks, so let's just try the other option. Task 2 is higher priority. Okay, so if I take task 2 as higher priority and I run it, and then task 1 runs, what will happen is, again, in this case, task 1 misses the deadline, right? Because task 1 deadline is the period, correct? So by 5 units of time, I have not completed task 1. Okay, so this is an example to show you what we mean by necessary but not sufficient. Okay, so u is less than equals to 1, yes. So it is necessary. So I fulfill the necessary part. Okay, but it is not sufficient. So just because u is less than equals to 1 doesn't mean I can schedule the task, all right, and fulfill the timing constraints. So it still may or may not be schedulable even if this condition is satisfied. All right, so that is the difference between what is necessary and sufficient. Okay, now, so you can see that a task may or may not be schedulable, okay, even if this condition is satisfied. Okay, and of course, what we then need to do is we follow these steps to analyze it based on the hyper period. So we assign priorities according to RMS, simulate the schedule for the hyper period, and then we check if any deadline is missed within the hyper period. All right, and if no deadlines are missed within the hyper period, then we can guarantee and say that it is schedulable. All right, so that is the other way of assessing whether a task set will be schedulable. So let's look at this again. So in this example, okay, I have two tasks. Task 1 period is 5, task 2 period is 7. Okay, and completion time is 2 and 4. So based on RMS, this is higher priority and this is lower priority. Okay, task 1 is higher, task 2 is low. So task 1 will run first and task 2 is going to run after that, and then you have a preemption here, and then task 1 runs, so task 2 misses the deadline. Okay, so within the hyper period, okay, if it is not possible, all right, then you can say very certainly that this task set is not schedulable, okay, using fixed priority. All right, so again the term right now is called if you see we are using fixed priority. All right, towards the end of the slides we will talk about another type of priority, which is dynamic priority. Okay, so that is a different type of scheduling approach. All right, so different OS may use different scheduling approaches. All right, so in this case we are talking about this particular analysis, which is fixed priority. That means when I assign a priority to a task, that priority will stay with the task throughout the entire life of the system. Okay, so as long as I do this hyper period check and I see that it is not schedulable, then you can say that this is not schedulable at all. All right, so this current approach to this program is not going to work. Okay, you will not have enough time to fulfill all the requirements of the various tasks. Okay, then comes to another parameter we can also check. So the other one is called the utilization bound. Okay, so we saw that we can calculate utilization, all right, based on the computation time over the period, okay, of each of the tasks, and then we add them together. And then we have another parameter, which is the utilization bound. So this utilization bound is basically a fixed number based on the number of tasks, n tasks. Okay, so this is a fixed number. Okay, so if I have 1 task or 2 tasks or 5 tasks, okay, I just substitute the n inside, I get a fixed number. If my utilization is lesser or equal to this utilization bound, this is a sufficient condition. Sufficient means what? That means if I fulfill this condition, then I don't need to check anything else. Okay, if I fulfill this condition, I don't need to check anything else. I'm guaranteed to be schedulable. Okay, but it is not necessary. Okay, so not necessary means I don't have to fulfill this, but if I fulfill this, it's schedulable. But just because I don't fulfill this doesn't mean I'm not schedulable. Okay, so again, let's look at the example. Okay, then we have a better idea of this application of these words. All right, so this is basically a table that tells you the this value here, the utilization bound value for different n values. Okay, so when n is 1 or n is 2 or n is 5, so all these are fixed numbers. All right, because you just substitute into this formula, you get these numbers. Now, let's look at example here. I have these 2 tasks, okay, T1 and T2. So since I have 2 tasks, I substitute n equals to 2, I get the utilization bound as 0.828. Okay, 0.828, okay, for 2 tasks. Then what do? I compute the actual utilization. So the actual utilization in this case will be 1 over 2 plus 1 over 3. Okay, so that is the computation time over the period of each task. I add them up together, I'll get 0.8333. Okay, so I can see that this number is greater than 0.828. Okay, which means I do not satisfy the utilization bound. Okay, I do not satisfy the utilization bound, but okay, if I follow RMS and I try to schedule it, okay, using RMS, you find that it is schedulable. That means I do not miss any deadlines for one hyper period. Okay, so this is what we mean by a case where I do not satisfy the utilization bound, but yet it is still RMS schedulable. Okay, it is still RMS schedulable. So this is uh, the other parameter we can look at. Okay, so if you were to summarize it, okay, what you can say is, if utilization is greater than 1, definitely not schedulable. Okay, if utilization is lesser than the utilization bound, definitely schedulable. Okay, is sufficient. Okay, a sufficient condition means is enough. If I can fulfill this requirement that the utilization is lesser than or equal to the utilization bound, it is guaranteed to be schedulable. The one in between is this, where the utilization is lesser than or equals to 1, okay, but my utilization bound is bigger, okay, but my utilization is bigger than the utilization bound. Okay, so in this case, it may or may not be schedulable. Okay, so of course, in this case, what we have talked about so far is looking at the entire sequence over one hyper period, okay, based on RMS, and then see whether any deadlines are missed. Okay, and then from there, we can know whether it is schedulable or not. Okay, so that is the in-between layer, okay, that we need to analyze. Okay, so for rate monotonic analysis, okay, is basically an analysis for task set that meet the necessary condition but not the sufficient condition. Okay, so let's look at this example here. If I have 3 tasks here, okay, let's look at this. I have 3 tasks, task 1, task 2, task 3. Okay, now the utilization, okay, is basically in this case is 40 over 100, okay, plus 40 over 150 plus 100 over 350. Okay, that would be the utilization. And since I have 3 tasks, okay, I substitute 3 into the utilization bound formula, all right, and that is 0.779. Okay, so this one is coming back to this here. You just substitute the n into this formula over here, you get the value for the utilization bound. So for 3 tasks, you can see that I do not satisfy the condition of the utilization being lesser than the utilization bound. Okay, so I do not meet a sufficient condition. Okay, I do not meet. So the next thing is, what I can do, I can try to look at it from one task at a time. Okay, so now what we're looking at is, how do I analyze it from a different perspective? Okay, if I look at it as just task 1, okay, so task 1 is the highest priority because it is the shortest period. So task 1 alone, if I look at utilization, it is lesser than the utilization bound. So no problem. So if my system only has task 1, it is schedulable. If my system has task 1 and task 2, okay, that means 2 tasks, 40 or 100 plus 40 or 150, it is still lesser than the utilization bound, it is still schedulable. Okay, but the moment I introduce the third task into the system, it fails this utilization test. Okay, but from what we know so far, even if I fail this utilization bound test, I can still be schedulable. Okay, even if I fail the test, I can still be schedulable. So how do I analyze this in a better way? Okay, so of course, right now what you've been looking at is always drawing out, okay, analyzing it from the time perspective and seeing whether anything is missed. All right, but we are now moving towards a more mathematical approach, okay, where you can easily put in the necessary numbers and then know whether it will work or not. So it's a lot easier than drawing it out. Okay, so let's go in that direction. So to go in that direction, there's another thing that we need to look at. So just now we talked about the situation of the worst case scenario. Correct. What we want to do is, we always want to measure whether the system can still meet the deadlines in the worst case scenario. So what is the worst case scenario? The worst case scenario is when you have a critical instance. And what is the critical instance? It is when the time when you release a task and you have to wait for the longest amount of time to complete it. And when will that happen? When you happen to release the task together with all of the higher priority tasks. Okay, together all the higher priority tasks. Okay, so So I mean, take for example, you want to do something, correct? Let's say you go to the shop, you want to buy something, correct? The best case scenario is you go to the shop, you are the first person in the queue, nobody else is there. Alright, what is the worst case scenario? The worst case scenario is you're hungry, but you go to the shop and just before you come to the shop entrance, another 10 people jump in front of you. So that's the worst case scenario, correct? Then you have to wait for everybody to finish ordering their food, then you can order your food. Okay, so that's the worst case scenario. So the same thing happens here. Okay, where just as you're about to be released, the task is about to release, all the other higher priority tasks are also released at the same time. Okay, so that is what you call a critical instance. Okay, so in this case, for example, I have 4 tasks. Okay, priority 1, priority 2, priority 3, and priority 4. Okay, and all of them are released at the exact same time. Okay, so what will happen is that all the higher priority tasks, okay, will end up taking up a lot of the CPU time, and the lower priority tasks may end up getting more and more delayed. All right, and this is what we want, like the worst case scenario, and see whether my lowest priority task can still meet its deadline. Okay, so that is what we're interested to find out. So let's look at this example now. Okay, the same 3 tasks, T1, T2, and T3. Okay, now, so in this case, we say that this is a critical instance for T3 because T3 is the lowest priority and it happened to be released at the same time as T1 and T2. Okay, so definitely since T1 and T2 are higher priority, they are going to get the first go at the CPU, and then at those instances when the CPU is free, then T3 will get a chance to run. Okay, so in this case, for critical instance analysis, we are going to look at the worst case response time of a task. Okay, so of course we already know some of these terminologies that the worst case response time must be lesser than the deadline. All right, then we look at all the tasks that are higher priority than task T. All right, and then okay, so these 3 points, what I will do, I will explain to you from the timing diagram. Okay, then we will come back to this. Okay, so let's look at this from the timing diagram. So you can see that I release all the 3 tasks at the same time. Time t equals 0. Then what would happen? Okay, definitely each of these tasks would have a periodic interval. Alright, so for example here, this is every 100 units of time. Okay, that I need to repeat myself. Similarly, here is every 150 units of time. And this is 350. Okay, so what is going to happen? So at every point of time, I need to look at which task is going to run, and then I need to see which are the other tasks that can potentially block my current task. Okay, so for example, if I look at T1, okay, so what I need to do is I need to look at all the periodic intervals of the higher priority tasks, okay, compared to the current task that I'm looking at T3. Okay, so that is the first point over here. For each higher priority task, find out the maximum number of task instances that may interfere with the deadline of T. Okay, so what I'm going to do is, since T3 is the lowest priority task, okay, I need to look at T1 and T2. Okay, and I need to look at how many instances of T1 and T2 would be released before the deadline of T3. Okay, so the deadline of T3 is 350, correct? So how many instances of T1 will be released? Okay, so for T1, I got 1 instance here, 2, 3, and 4. So there will be 4 instances of T1 that are released, all right, before the deadline of 350. So this is the deadline. Okay, this is T equals to 0, and this is the deadline of my task. Okay, now the next thing is for task 2. Okay, task 2 has a period of 150. So it will release how many times? So this is 1 time, 2 times, and 3 times. Okay, so there will be 3 instances of task 2 that are released before the deadline of 350. Okay, so that is what we are doing here. 4 instances of task 1 and 3 instances of task 2. Okay, and both task 1 and task 2 have the same computation time of 40. Alright, so that is basically the amount of computation time that has to be already set aside for the higher priority task. Alright, so within the deadline of 350, alright, I need to set aside 280 units of time, okay, that is required by the higher priority task. Okay, so what is the worst case response time of R3 or of T3? So the worst case response time is the total computation time plus the interference. I is the interference. Okay, so if you look back at the beginning slide, we talked about the worst case response time. Worst case response time and worst case execution time. Worst case execution time is the time, the worst case execution time is the time that you can take if you run your code, okay, and you probably execute maybe the loop to the fullest, you execute all the sections of the code or so on. All right, so that is the worst case execution time without any preemption or interference. Worst case response time is I execute a piece of code, but in between some other higher priority task can interfere. Okay, so I need to wait and then come back and then execute again and so on. So that is all the interference. So the worst case response time has to be within the period. Correct? That means even if I get preempted, higher priority task take over, I come back and I finish within my deadline, is still fine. Okay, so I need to check whether I can still finish within the deadline. All right, so for task 3, the total computation time is 100, but the total amount of interference is 280. Correct? This is the interference. So if I take the interference 280 plus 100, which is the computation time of task 3, I get a value of 380, which is greater than the period of task 3. Right? And period is basically deadline. Okay, so it's greater than the deadline of task 3. Okay, so if you look at this, all these calculations, all these numbers, we can sort of feel that task 3 is not schedulable. Okay, task 3 is not schedulable. Okay, but let's look at this a bit more deeper to see whether is it really the case or it's not. Okay, now let's look at this from more detailed timing analysis. So this is time t equals to 0. So at time t equals to 0, all the 3 tasks are released. Task 1 runs first. Okay, it computes 40 units of time, and the moment task 1 runs, of course, it gives up the CPU because the next iteration is here at 100 units. Correct? So this 100 and this another 100. So this 100, 200 and 300. Okay, so once it gives out the CPU, task 1, task 2 will get a chance to run, and task 2 takes up 40 units of time. Correct? And task 2, basically the deadline here is this. So this is 150. Okay, and this is the next 300. So this is the periodic interval of task 3. So what do you see here? When task 1 and task 2 both finish, there is actually a gap of 20 units of time before the next iteration of task 1. Alright, so that 20 units of time task 3 can take. Alright, because both T1 and T2 are not using the CPU, so task 3 can actually do some computation at that time. Then the next iteration of task 1 comes, again I take 40 units, okay, and then when I complete 40 units, this is 140 here. Okay, and the next iteration of T2 will only happen at 150, which means I have another 10 units of time that is free for the CPU to use. Okay, when task 2 finishes, it is again 190. So I have another 10 units of time that nobody is using, so task 3 can use. Then at 200, again T1 comes in and T1 completes at 240. Okay, and the next iteration of T1 is 300, and the next iteration of T2 is also at 300. So from 240 to 300, I have a total of 60 units of time that is available. Correct? And you add up all of this, you get 100. Okay, which is basically the computation time required by T3. So if you look at it, I actually can complete task tree, okay, in all those small gaps of time where the CPU is free, and still fulfill the deadline. Okay, I can still fulfill the deadline. Okay, so a detailed timing analysis actually tells us that it is possible to do this. Correct? Okay, it is possible to do this. But yet, our earlier calculation seems to suggest otherwise. Correct? In our earlier calculation, it suggests that it is not possible. But if you look at the detailed timing, okay, we look at all the gaps where the CPU is free, okay, we see that it is possible. Okay, so that means the way we calculate, okay, this approach needs to be slightly modified right now. Okay, this is too simplistic. We need to factor in these gaps a bit more carefully to see exactly when and where I can actually push T3 in to be used by the CPU. Okay, so that is where, okay, we are going to now look at it, okay, in a bit more detail. Okay, so what is the problem with the current computation is, okay, we only check at 350. Okay, what we did is we check at 350. Why? Because we see the deadline of task 3 is 350. Okay, and what happens at 350 is at time 300, both T1 and T2 released a new instance. Okay, but actually task 3 finished at 300 already. Okay, so because we included the fourth instance of T1 and the third instance of T2, this and this added into the calculation earlier on. Alright, but actually it's not needed because at time 300, I already finished my task tree. Alright, so that is the current problem. Okay, we looked at the deadline of task tree, which was 350. Alright, and then because T1 and T2 both release a new instance at time 300, that caused us to overshoot. Alright, and then we say the interference is too much. Okay, so in order to solve this issue, we need to be checking at more points. That means instead of just checking at 350, which is the deadline of task 3, we need to check at a few more points. So what are these points? We need to check at all the periodic intervals of the higher level tasks as well. So instead of just 350, we need to include all the periodic intervals of the higher level task. So whenever a new task instance is released, we need to check whether the total demand is less than equals to the capacity. Okay, the demand is basically the timing requirement for all the tasks, and the capacity is how much time has already been elapsed. Okay, so let's look at this. If I look at first t equals to 100, okay, if I just look at t equals to 100, okay, what do I get? I get that I have a demand, okay, of 40 units from T1, 40 units from T2, and 100 units of T3, because all the three tasks have already been released at time t equals to 0. Correct? So when time t equals to 100 comes, okay, just at that time, we already have these three instances there. Alright, and the total demand is greater than the capacity. So this is the requirement. Okay, this is the demand, which is the requirement for all the tasks, but the current time that has elapsed is only 100. Okay, so definitely you cannot fulfill. Next, I go to 150 because this is the periodic interval of T2. So at 150, what happens? I have released, okay, one instance of T1 and another instance of T2. So another instance of T1. So total is 2 instances of T1, 1 instance of T2, and 1 instance of T3. So again, demand is greater than capacity, so I cannot fulfill. At time t equals to 200, I have released 2 instances of T1 and 2 instances of T2 plus 1 instance of T3. Okay, so again the demand is greater than capacity, so I do not fulfill. But at time t equals to 300, you realize that I have released 3 instances of T1, 2 instances of T2, and 1 instance of T3. And at this time, the demand is 300 and the amount of time that has elapsed is also 300. Okay, so if my demand is lesser than equals to capacity, then it is schedulable at time t equals to 300. So this is what we need to do. Okay, we need to be able to check at all the different periodic intervals of the higher level tasks. Okay, so that is where that is bringing us to the next test, which is called the schedulability test, which is necessary and sufficient. Okay, so if I am able to check this, okay, and it's schedulable, then there is no issue. Okay, so this is the mathematical notation. All right, but instead of looking at this, all right, I'll go to the practical application side. Okay, then it's easier for us to see what we need to do. Okay, so what we need to do is we need to look at all the time instances to consider where or where we look at the periodic intervals of all the higher level tasks. So in this case, this is for task 1, and this for task 2, and this for task 3. Okay, so for each of the tasks, okay, what we do is we look at this J value, and this J value is basically the period of the lowest priority task over the period of the current task, and then I take the floor of it. Okay, so this is the J1, J2, J3, okay, up to the I number of tasks. Okay, so you calculate these 3 numbers, and then all you need to do is you take the you compute W3, okay, which is the total computation time, okay, required for the 3 tasks up to a particular periodic interval of the higher level tasks. Okay, so in this case, since the higher level task is having a period of 100 or 150, so we take all these different instances, all right, and for each instance, what you can do is you calculate that number divided by the period. So in this case, this is 300 divided by the period of task 1. This is 300 divided by the period of task 2. This is 300 divided by the period of task 3. Okay, so what you are doing here is you are trying to see how many instances of the low of the task have already been released at that particular instance of time. Okay, so what we are doing is previously we looked at it only from the perspective of the deadline of the lower priority task. Okay, but now what we are doing is we are looking at it from the perspective of the number of task instances that have been released at the periodic intervals of all the higher level tasks. So in this case, we are looking at 300. So at 300, we take 300 over 100 times 40, which is the computation time for task 1. This multiplied by 40 by computation time of task 2, and then by 100, which is the computation time of task 3. And we get a value of 300. All right, so if this timing deadline is lesser than equal to the computation time, then you know that you have fulfilled the timing requirement for the lowest priority task. That means you can still fulfill the deadline. Okay, so this formula here is basically doing what we did just now here. Okay, doing what we did just now here. All right, so of course you can analyze it based on a timing diagram like this. All right, you can draw it out and analyze it, or you can use the formula over here. All right, so of course in this case you need to consider different timing. All right, so in this case from the timing diagram we already know that 300 is the point where we saw it was able to fulfill, so we directly put in 300. Okay, but of course if you're not sure, okay, or you're not done the question before, you need to try from 100, 150, 200 and so on, and then see whether the computation time is less than equals to the demand, and whether if that is satisfied, then you are able to schedule the lowest priority task without any deadline being missed. All right, so that is the way in which you can analyze and get a better idea whether in a worst case scenario, which is a critical instance, I can still schedule all my tasks without missing any deadline. Okay, all right, so this is the last part of this chapter here. All right, so like I mentioned just now, up till now we have been talking about the fixed priority. That means once I fix a priority in a system, okay, for the task, you will carry on with that priority till the end. Okay, it is also possible to have a dynamic priority scheduling scheme, okay, where the priority will keep changing. Okay, the priority can keep changing depending on the deadline. Okay, so okay, so basically in a dynamic priority scheduling system, the task with the earliest deadline will have the highest priority. Okay, so what is the difference? In the earlier case, in the fixed priority, we say shortest deadline. That means we say that the task based on the information that we already have on the periodic intervals, the one with the shortest deadline is the going to have the highest priority. But in this case, it's a dynamic priority. So as the system is running, when a deadline is approaching, the one with the earlier deadline will automatically switch over to have the higher priority. Okay, so every time the priority keeps changing. All right, so let's look at an example over here. So I have two tasks here, T1 and T2. Okay, so if you look at it from the perspective of deadline, this T1 has a deadline of 4. Okay, and this T2 has a deadline of 10. Okay, so assuming that both of them now start off at time t equals to 0, the task which has the earlier deadline is T1. Okay, so since T1 has a shorter or earlier deadline, T1 will have a higher priority, so T1 will run first. So after T1 runs, then T2 can get a chance to run. Okay, okay, so there's a question. I'll come back to that question after I explain this. Okay, so for T1, okay, we say that T1 is a higher priority at time t equals 0 because T1 is a shorter deadline or earlier deadline. So after T1 runs, then you transition over to T2. Okay, so T2 will run. When T2 is running, okay, then T2's deadline is 10 units away. All right, so the deadline is still further away. So once T2 is up, the next instance of T1 will run. Okay, so when T1 when T2 is running, T2's computation time unit is 5 units. Okay, so when T2 is running, okay, what will happen is at time t equals to 4, the next instance of T1 will actually be released. Okay, so when the next instance of T1 is released, okay, the scheduler will look at who has the earlier deadline. Okay, so the deadline for T1 will be shorter because the deadline is over here compared to the deadline for T2. Okay, so since the deadline for T1 is earlier than the deadline for T2, you will preempt T2 and run T1 first. Okay, so T1 will run. Okay, when T1 runs and it completes, then T2 will run. Okay, so after that, I'll transition over and carry on with T2. Okay, so at this time t equals 8, okay, the next instance of T1 is released. Okay, but when the next instance of T1 is released here, what happens is the scheduler will see who has the earlier deadline. So the T2, all right, the deadline is over here at 10 units. Whereas for T1, the deadline will be here at 12 units. Okay, so since the deadline for T2 is earlier than deadline for T1, the scheduler will change the T2 priority to be higher than T1. Okay, so at the time t equals to 8, what will happen is the priority for T2 will be set to be higher than the priority for T1. So T1 will have to wait, okay, until T2 finishes. When T2 finishes, then at time t equals to 9, then I can transition over to T1. Okay, so when I'm running T1, Again, at time t equals to 10 units, what happens? Since the periodic interval of T2 is 10, the next instance of T2 would be released. Okay, so the next instance of T2 will supposed to be released at time t equals to 10. Okay, but what will happen is, because the deadline for T1 is earlier, correct? The deadline for T1 is coming in at 12 units here. Okay, the scheduler will allow T1 to have a higher priority than T2. So T1 will run first, and then I will transition over to T2. When T2 runs, again T2 computation time is 5 units. So when T2 runs, it will complete, but at time t equals to 12, another instance of T1 is released here. Correct. And for this instance of T1, the deadline is over here at time t equals to 16. Okay, which is earlier than this deadline, correct, of 20. Okay, because the deadline is every 10 units for time T2. Okay, so since the deadline of T1 is going to be higher at this point over here, you will preempt T2 and you will run T1 first. Then when T1 has completed, you will transition over to T2. Okay, and here in T2, okay, when you're running, at time t goes to 16, what happens? At time t goes 16, over here, another instance of T1 is released, okay, and T2 is still running. Okay, but at time t equals 16, what you observe is both T1 and T2 will both have the same deadline of 20. Correct? Because T1 has deadline is 4 units away, T2's deadline is also 4 units away at time t equals 16. So since both of them have the same priority, okay, there will not be any change, and T2 will carry on, and then T1 will get to run. Okay, so that is basically your scheduling approach for EDF. Okay, so in EDF, basically what you're looking at is the earliest deadline first. All right, so every task still has a periodic interval. Okay, and you're going to run it in this periodic interval. But at every instance where every time where a new instance of a task is released, you will look at the deadline of the current task that is already running and the deadline of the new task being released. Okay, if the new task deadline is going to be earlier, then that task will have higher priority. If not, the current task will carry on running. And then I'll switch over. So you will dynamically adjust the priorities, okay, based on the timing of the different tasks. Okay. So EDF is also what we call a optimal scheduling policy. That means if you are able to have a dynamic priority scheme, okay, for your if a feasible schedule exists using dynamic priorities, the EDF will produce a feasible schedule. Okay, and as long as utilization is less than equals to 1, EDF can definitely produce a feasible schedule. All right, so for dynamic scheduling, we say that this utilization less than equals to 1 is necessary and sufficient. Okay, for a fixed priority system, it is necessary, but it is not sufficient. Okay, but for a dynamic scheduling system, it is necessary and sufficient. Okay, so that is the main difference between fixed priority and dynamic priority. Okay, so of course each of them have their own sort of merits. Okay, and of course it's a lot more complex to look or design a dynamic scheduling system. Okay, so most RTOS and so on that we deal with usually have a fixed priority scheduling system. Okay, they may support different type of scheduling algorithms. Okay, but they do have dynamic priority in a sense where you have a case of the priority inversion, which I told you about. Okay, we will be looking at that in more detail very soon. Okay, but that is basically a temporary switch of priority. Okay, so let me come to the chat and just see all of the question. Okay, so the question was we only need to check WT for all time point the higher tasks are released within one period of the lowest priority task. Okay, yeah. So basically, what you want to look at is, okay, so if you, let me go back to the earlier slide here. Okay, so if you look at this, okay, what we want to do is we want to analyze the computational time required, okay, uh, at each instance where a new task or each time where a new instance of a task is released. All right, and then from there we try to see whether at any point of time do you actually satisfy the condition where the computation time is actually equal to the demand or to the capacity that you have. Okay, why is this important is because this approach actually takes into account these small gaps. All right, while not unnecessarily adding a new instance of a task which is not required. Okay, so if you look at this example, the issue is because at time t equals to 300, okay, we have the case of releasing a new instance of the task which was actually not needed at all, because by time t equals to 300 we already completed task 3. So by looking at it at each instance of a release of a task, we can actually analyze and see whether all these small pockets of time were fully utilized by the CPU to finish up the lower priority task requirements. Okay, so that is basically what we're trying to do here with this approach. Okay, so EDF is like a greedy algorithm. In a sense, you can say somewhat, but basically what we are trying to, what the processor will be trying to do is, it comes back to the idea of RTOS, correct? What we say is RTOS is supposed to be a system which gives the highest or gives priority to tasks which need the most urgent attention to make sure that we can fulfill the real-time constraint that we have. Okay, rightfully, if you have designed the system, okay, with the correct priorities for all the different tasks, then you do not need to have such a complicated scheduling algorithm. Okay, of course, if your OS supports a dynamic scheduling algorithm, you can try it out and see whether it works. Okay, and basically the advantage of that is, as what we say, if you can measure the utilization to say it is less than equals to 1, then your OS, if it supports a dynamic scheduling policy, then you can definitely guarantee that it's going to be schedulable. Okay. Okay, so do we need to check for all possible instances? No, as long as we are able to satisfy that at some point of time before the deadline. Okay, so basically, what if you come back here? Okay, it's not necessary that I need to go to all, correct? If let's assume that by time 200, okay, by time 200, I already am able to fulfill the condition where the computation time is less than or equal to the available time. Then is enough. Okay, so I don't need to go on to 300. As long as at some periodic interval of the higher priority task, I already satisfy this condition before the deadline of the lower priority task, then I don't need to check any further already. That means I know that I have sufficient time to complete the timing requirements of all the tasks. Okay, is it possible to emulate a dynamic scheduling algo by adding some chunks? Yes, you can do that, all right, but it just adds unnecessary overhead. Okay, usually when we take an OS, okay, unless you are doing research in scheduling algorithms or scheduling approaches or so on, then you play around with how the scheduler works and all these things. Okay, generally, if you look at it from the application perspective, when you take an OS, you choose an OS that you know has either real-time capabilities or fulfills those requirements, and then you apply that OS to solving your problem. Okay, trying to add another layer of complexity to how the OS works may just complicate things even further. All right, so it's better to start off with the OS that you think is going to fulfill your needs first, and then use that OS in the application aspect. Okay, so yeah, so that is basically the end for the scheduling algorithm. So I will take a short 5 minutes break now. Okay, we will come back. Okay, so when we come back, what I will do is the next set of slides, I will not go through everything. I will go through just the first part until the mutex, and then we will go over to the lab manual for this week, so that I can talk to you about what you're going to see in the lab and what are the reasonings behind the observations. Okay, so I'm just going to go through the first part until the mutex only. The semaphore part, I will leave it to next week. Okay, so we'll come back in another 5 minutes, and then we will go through the next set of slides, okay, until the mutex. Okay, so I'll see you back here, okay, in 5 minutes time. Okay, so let's carry on. Okay, so the next topic that we're going to be discussing is on this called concurrency. Okay, so before that, there's two things I wanted to say. Firstly is on the project, the LED strip. Okay, so I saw some of you all connecting up the LED strip with a lot of resistors. Okay, but basically, if you look at this connection here, you don't need individual resistor for each LED. You can just short all the cathodes together and just have a single resistor. Okay, that will simplify your design a lot. All right, so you can practically just solder the entire cathode layer together with a single wire and just have one resistor coming out. All right, so again, you try to think of a simpler, more easier way to do things. Okay, so that your circuit is again simpler, neater, all right, and it's easier to prototype. Okay, so this is just something I want to show you because I saw some of you connecting up individual resistors for all the LEDs. Okay, but it's not necessary. Okay, whether it's you are going to run it across, okay, or you're going to run everything together, either way, a single resistor will still be enough. Okay, will still be enough. So that can simplify your design. Okay, so that is the first thing. The next thing is the actual maze setup. I will more or less finalize by this week. Okay, but one thing you will see is you will see ramps. Okay, so again, this is DSA lab is just the best place to be in, correct? So I went there yesterday to look around to see what I can do, and and Jalil suddenly told me, hey, we have ramps. Why don't we use ramps? I said, okay, why not? Okay, so we will be setting up this kind of ramps, okay, on the floor. Okay, so my current plan is there will be at least 2 ramps for your robot to go up and down. All right, and then besides the ramps, I will put some cones for you to do some zigzag operations. Okay, that means something like there may be a cone over here, another cone over here, and your robot may be asked to do a S or a figure 8 or something like that. Okay, so these are just giving you some heads up on the kind of things that your robot will be expected to do. Okay, so I mean, you are in total control of it, okay, through your phone. All right, so you do not need to worry about having any sensors to detect anything. So as long as you are able to control it well, okay, you shouldn't have an issue to maneuver and go through all of these obstacles. Okay, so the actual layout, how it's going to be, I will let you all know soon. Okay, but you can expect at least 2 ramps. Okay, that look like this, and a few cones for you to go around. Okay, the black line is not needed. This black line is there because previously these ramps were used for earlier project. This was many years back, where they had a line following robot. Okay, then you need to So that's why those lines were there. Okay, we don't need to worry about the lines. Okay, if you have multiple LEDs connected to the same resistor, okay, if you make, okay, and you drive all the LEDs together, okay, what will happen? Basically, they're all going to share the same common pathway down, correct? It will be fine, okay. Basically, from what I showed you, there is no particular issue with that, okay. Of course, I'm not saying if you still want to put individual resistor, it is fine, okay. But from what I saw, if you think that it's too dim, you just lower down the resistor value, correct? Okay, so you can always play around with your hardware to get the effect that you want. Okay, so if doing this, you say that your resistor value is too dim. Okay, when I try to light up all together, then try to lower down your resistor to something even smaller. Okay, so I mean, at the end of the day, it's up to you. Correct. Okay, I'm just giving you options. Okay, to sort of maybe make it a bit easier or simpler for you. Okay, but if you still want to go ahead and do individual resistors, that is also fine. Okay, another thing that I mentioned in the announcement is also if you want to do any hardware prototyping, you can always ask, tell me, or Uncle Jalil will give you the hardware stuff. Okay, so in terms of hardware prototyping, we have strip boards. If you remember strip boards for EPP2, basically you have individual solder pads and then you can connect them up together. Okay, or the other option is we have Vero board. Vero board is where everything on a single line is connected together. Okay, so we have different type of prototyping boards. Okay, so if you think that you want to transition your hardware to onto boards, okay, with soldering and everything, we can do that. Okay, so again, these are just options. These are not compulsory. You are not going to be given additional marks because you did soldering. No, okay, because these are not the things that we are testing you on. Okay, so these are just things for you, so you feel happier, you feel you did a better job. Okay, because anyway, like I said, the robot is for you to keep. Okay, so you can do what you want. Yes, the assessment will be based on the checklist requirements, okay, as well as the maze run. Okay, this hardware prototyping, to what extent you want to enhance it or what is up to you. Okay, so let me go on to this topic proper. Okay, again for mini project, okay, any questions, I'll leave it to the end. Okay, so that we finish the material first, and those who want to stay back and ask me any questions, I will clarify later. Okay, so let's go on to this first. Okay, okay, let's have just a quick overview on what is the idea of multi-processing. Okay, so in a single hardware and single threaded environment, okay, usually what we say is we have a single instruction and single data stream. That means when I fetch the instruction, okay, so in this case when I say fetch instruction, I'm talking about a assembly language instruction, for example, from memory. Okay, so in that instruction, for example, I add, okay, and I say R0, R1, okay, 500. Okay, so I say I give you some assembly language instruction. So that instruction, okay, will be fetched and sent to the processing unit. All right, and of course, as part of the processing, you may get data from memory as well, or from the cache, and then you process it, okay, then you get some result. Okay, so that is the single instruction, single data stream. You also can go on to another option called the multiple instruction in a single data stream. Okay, so multiple instruction single data stream could be uh, the, uh, the situation where you have uh, a single line, okay, or single data where you want to perform multiple different operations on it at the same time. Okay, so there can be processes where instead of just add, okay, you may have complex type of instructions where you can tell the processor to do a few different things, okay, to the same set of data at the same time. All right, so in those cases you will have your hardware may have different processing units, and then you take the same data, all right, but you send it to different processing units to carry out different instructions. Okay, another variation is single instruction, multiple data streams. Okay, so for example, if you do audio processing or image processing, okay, every time you take, for example, in images, okay, so if I take a picture, for example, for every pixel, if I do a processing, I may need to look at all the surrounding pixels as well. Okay, and then do some processing on all of them at the same time. Okay, so I have a single instruction, but I need to process multiple data at the same time. Okay, so of course at the very extreme end, you have multiple instruction and multiple data streams. Okay, so this is in cases where you have a lot of different processing units that can process a lot of different data at the same time. Okay, so all of this, as you can see, involves variation in the way the hardware is wired up. Okay, so in general, okay, when we say single instruction, single data is the kind of approach that we'll be looking from a, for example, a simple microcontroller. Okay, it's sequential. There is no parallelism involved. Okay, and concurrency is basically at the hardware level. In single instruction, multiple data is, for example, you have, for example, GPUs. Okay, where you can have a single instruction, but you are processing a lot of data at the same time. Okay, like what I mentioned, if you are dealing with graphics or images or audio, every time you do a signal processing expression or equation on a particular point of data, you may need to also uh, reference the surrounding data points. Okay, so you want to be able to do the same instruction on a group of data at the same time. Okay, so you can have dedicated hardware units that can do this for us. Okay, so that is where your GPUs and graphics cards, all of these come in, right? Because their hardware is configured to do this kind of processing very effectively. Okay, multiple input, single data is not something that you see quite, or not, is rarely used. Multiple input, multiple data is basically the idea of like multi-core systems. Okay, where you have multiple instructions, so multiple processors executing different instructions and different data all concurrently, because you have so effectively like multiple processors all running together, but each of them doing different things at the same time. Okay, but you want to sort of be able to collect the response. Okay, and of course all these hardware solutions require a lot of back-end work, because the software must also be able to take advantage of these hardware improvements or changes. Okay, in many cases, okay, in the past especially, hardware advanced much faster than software. Okay, so even though we had hardware improvements in terms of dual core or quad core processors and so on, we didn't see much improvement in the actual execution of many applications, right? Because the software was not yet optimized to take advantage of this additional hardware available to us. Okay, but of course now we have come a long way, where we have software that is able to do this, correct? So it is able to know that, okay, I have a hardware that I have a graphics unit or have a dual core system. How can I make better use of this hardware? Okay, so now software has sort of been able to catch up with the advancement in hardware. All right, so that is why you are seeing a lot of improvements in your processing capability of not only your handphones, correct? Even your laptops, your desktop, everything over the past few years. Okay, so for our case in this module, we are going to be focused on operating systems on a single processor. Okay, so we're going to be looking at things like the scheduling policy. We already looked at it. All right, now we're going to be looking at things like the memory and data management. Okay, how do you handle this kind of aspects when your OS is taking over the execution of your code? Okay, so let's look at it from a single-threaded versus multi-threaded approach. In a single-threaded environment, okay, so for example, it's just a single while loop, all right, or a single function. I have a piece of code that is going to write to a memory location, all right. In a single-threaded environment, there is no particular issue. Of course, the only challenge that comes about is I have an interrupt. Okay, in a single-threaded environment, the only other way in which things can go wrong is the interrupt is also trying to write or read to this same data. Okay, it is a global variable, and both the main loop and as well as the interrupt are both trying to get access to it. Okay, so of course that is also an issue. But in a multi-threaded environment, this can happen a lot more easily. Okay, because the data can be shared among multiple threads, correct? And you do not know exactly when you're going to get switched up. Okay, and anytime you get switched up, all right, one thread could be in the middle of doing something while the other thread suddenly came in and took over. Okay, so all these are potential issues, okay, that we need to learn how to deal with. Okay, so in concurrent systems, okay, the results, okay, of the computation, it depend on the exact way the processes interleave. Okay, if not, we have what is called a race condition, where one process is trying to access the data or in the middle of accessing the data, and halfway it gets preempted, and another process is now going to access or deal with the same set of data, but what has happened is it is now not complete. Correct? Okay, so for example, okay, you have an array. Okay, so let's say I have 1,000 byte array. Okay, and task one's objective is to take this. Okay, so let's assume that maybe I take audio data, okay, and I'm supposed to write. So this one task is supposed to write to this 1,000 byte data, and task 2 is supposed to read from this data, okay, do some signal processing. Okay, this is task 2. Okay, and after this processing is done, it's supposed to write back. Okay, so if task 1 was running, okay, and halfway through you get preempted. Okay, so task 1 was writing, okay, and halfway through you get preempted, and then task 2 gets a chance to run. Okay, if task 2 does not know that task 1 was in the middle of it, correct, and task 2 just goes ahead to take this data and write back, then what will happen is when task 2 finishes and comes back, then the whole data is all messed up now. Correct, you have half data which was written, then the data that was processed is half written, half not written with the updated value and so on. Okay, so these kind of situations can occur, okay, for shared data along with multiple tasks. So we need to make sure that we handle them correctly. Okay, so for example, this, okay, so in this case we have a shared variable called k. K is a global variable, and I have a function increment k, which is to say k equals to k plus 1. Okay, and both function a and function b are both calling both function a and function b in this case are threads. So this function a and function b are both thread a and thread b, and they are both calling a common function called increment k. Okay, so what is going to happen? So the first thing we must understand is the code k equals to k plus 1, okay, it is not considered an atomic operation. That means it is not considered a single line statement, because even though in C it is considered a single line, in assembly language when you translate it, it will translate into a few assembly language instructions. Okay, in general at least 3, because you need to fetch the data. Okay, then after you fetch and decode everything, then you execute, which is the addition, and then you do a write back. Okay, so you fetch the data or fetch the instruction, perform the execution, okay, which is the addition, and then you do a write back. Okay, so in assembly language, you are talking about at least three assembly language instructions, okay, for a single C statement like this. Of course, it may vary, okay. Generally, for RISC systems, okay, which is like, for example, ARM-based systems, you can say that this is what you can expect. Okay, it is possible, okay, that if you are dealing with a CISC processor, that this C statement might translate to a single assembly language instruction in a CISC processor. Okay, it is possible. Okay, but again, we should not make an assumption of how the processor might behave. Rather than that, we should follow the correct procedure of how to deal with shared data. All right, so that regardless of whether it's a RISC system or a sys system, we are still able to run the code correctly. Okay, so since we see that a single line in C like this, k equals k plus 1, will translate into a few assembly language instructions, what can go wrong? Okay, so let's look at it. So in the first case here, okay, so let's look at this first. So we are going to do parallel execution on 2 CPU cores, where so in this case what we're going to do is we're going to say that this CPU 1, okay, is going to read and write or execute this instruction k equals to k plus 1, and in this CPU 2 we're going to do the same, k equals to k plus 1. Okay, now let's see what is going to happen. So rightfully, if I were to run both these codes, okay, my initial value k equals to 0, the expected value should be k equals to 2. Okay, that means k equals 0. If I execute k equals k plus 1 2 times, the final value should be k equals to 2. All right, so in this case, that would be the case if the sequence was like this. Okay, that means I first, okay, so in this case CPU1 and CPU2, okay, maybe you can just simplify it as maybe thread 1 and thread 2. Okay, so if thread 1 loads the current value, okay, it increments it, then it writes back. Okay, so what will happen is from 0 it become 1. Then the next task comes in, so it takes in a value of 1, increments it, then write back, so it become 2. Okay, so the very first time 1.1, 1.2, 1.3 is transitioning from 0, add 1 and write back a 1. Then 2.1, 2.2, 2.3 is load a 1, increment and write back a 2. Okay, but in a situation where you are preempted halfway, okay, so for example, I load the current value. So initial value is 0, so I load a 0. Okay, so I come in and increment, so 0 become 1. Okay, but before I can write back the task 1, okay, gets preempted and I switch to task 2. So task 2 also loads a value of 0. Then increment 0 to 1. Then I switch back to task 1. So I write back a 1. So from here it become a 1. Alright, and then task 2 comes in, it also writes back a 1. So again, I write back a 1. Okay, so in a situation where your task can be preempted halfway through the completion of this execution, you end up in a case where your final result is not what you expect. Okay, it's not what you expect. Alright, so this is basically what we mean by the race condition. Okay, so the critical thing to understand is the issue may not present itself all the time. Okay, because in a multi-threaded environment, we may not really know when the task switching is going to happen. Okay, because you can have multiple tasks all running concurrently, a lot of context switch is happening. Okay, so you cannot necessarily say when this kind of situation will happen. So you may run the code and everything is going well, and suddenly something is wrong. Okay, the data is not quite correct. Okay, so it may only present itself at some time. Okay, so it's very non-deterministic. So this makes it very hard to find and debug. Okay, now how do we eliminate these kind of race conditions? Okay, so what we need to do is we need to define what is called a critical section. Okay, so a critical section is basically a region of code where you are accessing shared resources. Okay, and why is this important? Because when I have shared resources, that means I want to make sure that if one task is accessing this shared resource, it does not get even if it gets preempted. Okay, we cannot stop the preemption because that is the whole idea of multitasking. Correct? The whole idea of multitasking is if suddenly somebody more important comes along, that person must be allowed to run. Okay, so that multitasking will still happen, but in a situation where you are in the middle of using a shared resource and you get context switched out. Okay, you want to be able to prevent another task from accessing this shared resource because you are still in the middle of using it. Okay, so these regions of code where you're accessing shared resources are what we call critical sections of the code. Okay, and you want to define this critical section and you want to protect this critical section using what we call a mutex. Okay, and basically mutex stands for mutual exclusion. And the whole idea of mutual exclusion is you enforce to ensure only one thread of execution can have access at any time. All right. So the good part is when one task takes exclusive access, even if you get context switch out, okay, and some other task tries to access it, okay, the task that preempts you can still run, okay, but if it tries to access that shared resource, then it will not be able to get that shared resource, okay, because you have already sort of locked it. Okay, so you can think of it as a lock and key mechanism. Okay, so one task will lock it and hold the key. All right, when it is done with it, it will sort of unlock and release the key. Then some other task can grab this key. Okay, so if you, another task tries to get this resource and you cannot get it, you'll go to a block state. Okay, you'll go to a block state. So that sort of forces the task to ensure that if I only can carry on with this shared resource, then I have no choice but to wait until the task that is currently using this shared resource gives it up. Okay. So let's look at this example here. So in this case, for example, okay, so in this case, thread A and thread B, okay, both of them, okay, so this is thread A and thread B, both of them want to run the code called increment K. Okay, both of them want to run this code called increment K. And now I am going to protect this code with a mutex. Okay, I'm going to protect this code with a mutex. So when I say I protect this code with a mutex, it means that whenever I want to run this function, I must do a lock. So if a task wants to run this function called increment K, I must lock the mutex. When I finished, okay, when I finished, then I will unlock. Okay, so these are the rules that must be followed. Okay, and these rules must be implemented by the programmer. Okay, the OS cannot enforce the rule. Okay, the OS cannot enforce the rule. It is the programmer who must enforce the rule. Okay, okay, it's just like, for example, you have your own room, correct, in the hostel. So if it's a own room, you have a key to it. All right. So rightfully, since you have the key to your room, you will lock it and you will unlock it. All right. So if everybody follows this rule, then there's no problem. Correct. But what if one fella tries to be funny and says, so what if you lock it? I will break the window and go in. Correct. So he can still go in, but he's not following the rules. That's why he can go in. All right. So that's what I'm saying. So everybody must follow the rules. Then everything will go well. If one person decides not to follow the rules, then things will get messed up. Okay, because following the rules is enforced by the programmer, not the OS. Okay, so I will show you the example later when we look at the lab. Okay, so in this case, okay, when task A is running, okay, and since task A wants to run this increment K function, it needs to lock. Okay, so in this case, we need to call this function called mutex lock. Okay, so when I call mutex lock, okay, I'm basically locking the access to this function called increment K. But now what is happening is the moment I do a mutex lock, I have a context switch. Okay, so maybe task B was blocked, task B is higher priority or whatever, and suddenly task B starts to run. Okay, so thread A has locked the mutex, but before it can run the function, it got context switch out. Okay, and then thread B runs, and thread B also wants to use increment K. So thread B is of course following the rules, so it tries to do the lock. Okay, and since somebody else has already locked the mutex, okay, somebody has already locked the mutex, okay, the OS will now put this state into a block state. Okay, put this thread into a block state. Okay, because you are trying to acquire a resource and you are unable to get it. Okay, whenever you try to get a resource and you're unable to get it, you will go to the block state. So the OS knows that you want to lock the mutex, but you cannot get it because somebody else is holding on to it. So you will go to the block state. When you go to the block state, if you look at the state transition diagram, when you go to the block state, automatically somebody else will transition to the run. Okay, so of course now we are just talking about two different tasks. So assuming that there's nobody else, so task A will be able to transition back to the run. Okay, when task A transition back to the run, it can now carry on, and since it already had locked the mutex, it can execute the increment k function. So in this case, this increment k is basically what we call the critical section of the code. Okay, because it is shared by both task A and task B. And once I complete the increment k function, I release the mutex. Okay, when I release the mutex, what happens? Okay, when I release the mutex, it will go to the task that was blocked waiting for it. Okay, so this is not shown here, but basically since task B was blocked waiting for the mutex, the moment I release, the mutex will go to task B. Okay, and once the mutex goes to task B, what will happen? The state will transition from blocked to ready. Okay, once the mutex that it was waiting for is now being acquired, it will automatically transition from block to ready, which means the scheduler will now see whether I should transition to thread B or should still carry on with task A. Okay, so this sort of ensures that whoever wants to execute this increment k function must lock the mutex first, then I execute, then I unlock. Okay, so in this case, if you are preempted halfway, like in this case, you do not need to worry. Nobody else can execute increment k until you have finished executing increment k and you release the mutex. Okay, so that is the whole idea of mutex. That means you are locking it, making sure you have access. If you get preempted out, no issues, you will still have access. Okay, when you come back. Okay, nobody else would have come in halfway. Okay, and then when you finish, then you unlock. Okay, for the mutex routines in RTX OS, basically these are things you need to do. Okay, you need to first declare a mutex globally. Okay, then you create a new mutex with this function OS mutex. Okay, different OS have slightly different terminology. Okay, some will say lock and release. Okay, in our case, it is acquire and release. Okay, so you just need to look at the online documentation to know the exact functions to use. All right. So in this case, it is acquire and release for RTX OS. Okay, so these are the main mutex related functions. Okay, and the idea behind it. Okay, so let me go over to the lab, okay, and show you the demo that you will actually be running this week. Okay, running this week, so that you know what to observe and what you're going to be seeing. Okay, so this is the lab manual for this week. Okay, so the first part is on the priority. Okay, so in the last lab we created the two different threads with the same priority. Okay, in this week's lab, the first part is to change the priority. Okay, so that part I will not go through. I'll leave it to you to go through. Okay, everything is explained clearly there. So in the second part is where we're going to introduce the mutex. Okay, so in this second part, I introduce the mutex. Okay, the sample code is already given to you. okay, where you create the mutex, okay, and I have two LED threads, okay, mutex new creator, LED red thread, LED green thread. Okay, so let me, so all the code is given for the first part here, which is also over here. Okay, so as you can see, the LED green thread is here, LED red thread is here. Okay, they are both the exact same code where I will, okay, let me zoom in. Okay, so I will acquire the mutex, okay, control the LED, okay, and then I will release the mutex. Same thing for the red LED. I will acquire the mutex here. Okay, okay, so this part I will comment. Oh, okay, now we don't worry about this part first. Okay, so basically I will acquire the mutex and then I will control the LED and then I will release the mutex. Okay, maybe I will. Okay. Okay, so let me make the code the same. Okay, so both the LED threads are now the same. Okay, OS mutex acquire. Okay, and then I control the LED and then I release. Same thing for the green. Okay, so if I were to run this code, okay, everything else being the same, which is I have LED red thread, LED green thread. Okay, so what do you think will be the outcome? Okay, so there's a poll there for you to see. Okay, so the code, as you can see, is basically LED red thread, LED green thread. Okay, red is created first, followed by green, and then I have a new text that is created here. Okay, and over here, for each of the threads, I do the same thing. I lock the new text, I on the LED, off the LED, then I release. Over here, the same thing. For green thread, I lock the mutex, then I on and off the LED, and then I release the mutex. Okay, so what do you think will happen? Okay, so again, think back at the idea of why you have a mutex. You want to protect access to a shared resource. Okay, you want to protect access to a shared resource, which means that when I'm accessing a resource, I want to be able to say that if I get preempted out, okay, or context switch out, it doesn't matter. I will still have access to it until I release it. Okay, so most of you have voted. Okay, so let's look at the results. So in the results, basically majority of you, okay, 70% have voted that it will be red first, then green, okay, and then you repeat the sequence. Okay, some of you have other ideas, okay, other thoughts. Okay, so let's look at it. Okay, so let's look at what's going to happen. Okay, so let me run the code. Let me compile this first. Okay, so you can see that it's first red and then followed by green. Okay, red, green, and so on. Okay, so why is it red, green, and so on? Okay, so maybe let me draw the timing diagram for you all. Okay, so why is it like this? Okay, so basically you have two threads, correct? One is the red LED thread, the other is the green. Okay, so we know that the red LED was created first, all right? So of course, when both are created, both of them are in the ready state. Okay, but since red was created first, it will transition to the run first. Correct. So when you transition to the run, what will happen? You will go in and you will acquire mutex. So I will just put it as lock. Okay, you will lock the mutex. Okay, and then you will start to blink the LED. Okay, we know from the last week's lesson that lab that you do not wait, correct? Because of the OS round robin behavior, I will actually do a context switch. That means halfway through here, while the LED is on, for example, I will actually try to do a context switch. Okay, so I will actually do a context switch and I will run. Okay, but when I run over to the green or and transition over to the green LED thread, okay, what will happen is okay, in the green LED thread, if you look at it, the first thing that I try to do is I try to acquire the mutex. Okay, I try to acquire the mutex. So since I try to acquire the mutex, okay, so when I transition over and I try to do a lock, okay, I will, the OS will tell me that I cannot lock it because somebody else has locked it. Okay, which means that I will transition to the block state. Okay, since I'm transitioning over to the block state, then I will be able to do a context switch back here. All right, and I will just carry on running, okay, whatever that I'm supposed to do, blink on, off, everything, until I do a unlock. Okay, when I do the unlock, okay, then the OS will look at, okay, which other task was waiting or has become blocked because it was waiting for this mutex lock. Okay, so you will know that the LED green thread was waiting. Okay, so the moment it unlocks it, okay, it will automatically give this key over to the task LED green thread, which means I will now transition from the block state to the ready state. Okay, and then I will be able to transition to the run. Okay, when will I transition to the run? It may happen immediately or it may transition or I may still be running it. So I cannot say I will immediately transition to run, but I know that I will go to the ready state. All right, and once I transition to the ready state, all right, I also have the mutex with me. So at this point of time, two things have happened. I've actually locked the mutex and I've also transitioned to the ready state. Okay, so when this thing happens, okay, when the LED red thread releases the mutex, okay, when the LED red thread releases the mutex, two things happen automatically. Okay, firstly, LED green thread now has locked the mutex because I was waiting here. Okay, so I will automatically lock the mutex and I will also transition to the ready state. Okay, I may not run immediately. Again, that is a decision by a scheduler, correct? Because of the round robin, it will decide when to run. Okay, so if let's assume that I actually try to run here again, then what would have happened? Okay, assuming that red is still carrying on to run, then what would happen is when the red tries to run, after I finish the mutex release, I go back to the beginning of the loop, which is I try to acquire the mutex again. And now what has happened? The mutex has already been locked by the green thread. Okay, it's already been locked by the green thread, which means that now the red thread will go to the block state. Okay, which will allow the green thread to run. Okay, so that is why. Okay, so of course when green thread starts to run, then it will also blink. It is on green LED. Okay, so that is why you're actually able to see the red blink first, and then green blink, and then red and green, and so on. Okay, so even though it is just red and green blinking, but it's actually a lot of things going on in the background because of the way the mutex is behaving. Okay, so that is something you must understand. Now, what is happening in the background? Okay, that is allowing the red LED to run first, and then the green LED, and then the red, and so on. Okay, so that is how the mutex is actually working over here. All right, so this is the first thing you will see in the lab. Okay, to understand and observe this behavior, and of course understand what is happening. Now the next thing that I ask you to do in the lab is to look at the rules. Okay, so like what I mentioned just now, everybody must follow the rules. What is the rule? The rule says I must lock the mutex. Okay, do what I want to do. Okay, and then I release the mutex. Okay, I must lock the mutex, do what I need to do, then I release the mutex. Okay, so now if I were to not follow the rules, okay, if I were to not follow the rules, okay, that means for example LED green thread, I comment off the OS mutex release. Okay, so let's go to the code over here, and okay, LED red thread is following the rules. Okay, it lock, control the LED, and then it release or unlock. Green thread lock, control the LED, but now I say I am not going to release the mutex. Okay, now if I were to run the code now, what do you think will happen? Okay, let me relaunch the poll. Okay, think about it first, think about it, and then you answer. Don't rush into it. Okay, so the scenario is the same. Only thing is the green LED alone is not green LED alone is not releasing the mutex. Okay, so let me end the polling now. Just okay, sure. So let me share the results. Okay, so the results, majority of you have said red will blink one time, green will blink one time, and then I only repeat the green blinking. Okay, so of course this is natural from our understanding of how lock and key should work. But let's just see whether that is what we're going to observe. Okay, let's just see. Okay. Okay. So this is the old code. Okay, let me load the new code in. So I'm going to compile this first. Okay, and then we're going to run this. Okay, so let's observe carefully what's going to happen. Okay, so red one time, green one time, and then nothing else. Okay, red one time, green one time, and then there's nothing else. No other blinking, no other LED. Okay, so why is it like that? Okay, we only saw one green LED. Okay, so let me run again. Let me reset and let me run again. So red LED one time, green LED one time, and that's it, nothing else. Okay, so the behavior is a bit different, correct, from what most of us thought. Okay, from what most of us thought. Okay, so why is it the case? Okay, so why is it the case? So let me explain this idea again. Okay, so in this case, okay, what happened was the red LED did it correctly, right? Okay, and after that the green LED. So everything, so this first part here that you see is still valid, all right? So the red LED blink, but after the red LED blink, what happened? It tried to, it did not release, correct? It did not release. So if it did not release, what happens? Okay, if it did not release, if you look at the code, okay, what happens is it tries to go back. When it goes back to the beginning of the loop, it tries to acquire the mutex again. Okay, so this is the interesting thing. I think most of us have this idea that since I already locked the mutex, okay, even if I don't release, it still belongs to me. Okay, true, it does belong to you, but as far as the OS is concerned, you are still executing another lock command. You are trying to acquire a mutex. You are telling the OS, I want to acquire a mutex. So the OS does not care whether you have it or somebody else have it. It just looks at what is the instruction. The instruction says lock this mutex. Okay, but as far as the OS is concerned, it has already been locked. Okay, so when you try to lock something that is already been locked, that means you are trying to acquire a resource that has already been locked by somebody. Okay, even though it is by yourself, it still doesn't matter. So you're trying to execute a lock, but the lock is not successful. So as far as the operation is concerned, okay, the OS mutex acquire operation is concerned, the result of the operation is that it's a failed operation. It's not a success. Okay, so it will say that you are unable to successfully lock this resource, so it will put you into a block state. Okay, it will put you in a block state. So that is how the OS behaves, because the OS looks at each OS call. So the OS mutex acquire call says, I want to lock this mutex. All right, and the return value. Okay, so what I would encourage you to do is after the lecture is over, when you're free, go to the online documentation to look at this mutex acquire, mutex release, and look at the return value, the return of this function to understand what is happening. So the return value will tell you that it was not a success. Something went wrong. So as far as something went wrong is something has gone wrong, it will put you into a block state. So if it goes in a block state, you cannot run. Okay, and since the red LED is already in a block state, it also cannot run. Okay, so eventually both the tasks are just blocked forever. Okay, so the thread, yes, so the thread itself locks the resource, but it cannot run. Okay, because you try to lock it again. If you did not try to lock it again, okay, if you did not try to lock it again, then no problem, you can still carry on running. Okay, the issue is because you try to execute the mutex acquire one more time. So as far as the OS is concerned, when I execute this command, OS mutex acquire, okay, it will not be successful. Okay, it will be a failure. So it will put the current task into a block state. So it will not allow you to carry on with the execution. Okay, you can still carry on. Okay, if let's say you had other code, okay, if after this mutex release, if let's say you had other code down here, no problem. You can still carry on as long as you want. But the moment you try to execute this command again, it will say that this command is not successful. So it will put you back into a block state. Okay, so it does not relate back to the fact that you are the one who actually have the mutex. It just looks at this particular command. You try to acquire this mutex, but you have not been able to do it. Okay, because this particular command has failed. So it will put you into a block state. So what will happen is both the tasks end up being in the block state and both of them cannot run. So that is why you only see red LED one time, green LED one time, and after that nothing else. Okay, so that is basically what you will observe for this week's lab. Okay, so go and try it out first. Okay, next week's class I will also explain this again. All right, in more detail. Okay, for you to have a better understanding, and the tutorial next week tutorial question will also look into this in a bit more detail. Okay, so again my apologies for running late today. Okay, so the question, okay, so there's two questions. The OS give error. Okay, correct. The OS will give us an error that something has gone wrong. Okay, and in the tutorial question, we will be exploring this. Okay, how to better handle a situation where there is an error, what to do or what not to do. Okay, so in the tutorial question, which we will cover next week, I will discuss this. Okay, on how to better handle the OS error messages so that you do not end up in a situation like this. Okay, so is everything is blocked, nothing runs? Yes. So if everything is blocked in this case, the only thing that runs is basically your OS idle task and your OS timer task. Okay, so both your LED tasks will not run. Okay, you can use as many resources as you want, multiple mutex, whatever, yes, is fine. The mutex itself has a few different possible configurations. Again, we will look at that next week. Okay, if you look at documentation, you will see what I'm talking about. Okay, the mutex itself has a few properties you can configure to alter this behavior. Okay, but again, those add more complexity to the behavior, which may not necessarily be consistent with how mutex is generally viewed. Okay, so if you want to change the behavior of a mutex scan, all right, with the properties, you have some free play into that. Okay, but we have to be very careful on what we do, because then the idea of how a mutex is going to work might not be consistent. Okay, so in the next week's tutorial, I will actually be talking about this more. Okay, how the two things. Okay, how to better handle error messages from the mutex, and also how to configure or look at mutex or use mutex in a different way. Okay, besides what we just saw this week. Okay, so I think no other questions. Thank you very much. Okay, so for the anyway, I'll send an announcement on the midterm to remind everybody on the things that has been announced so far. Okay, thank you. Bye.